Today on Why This Universe, we're talking to you about the latest neutrino discovery to come out of the IceCube experiment. This discovery was made back in June of 2023, and this is not our first episode covering neutrino discoveries like this one. Back in November of 2022, we reported on a discovery of neutrinos coming from a nearby galaxy NGC 1068. That was episode 56, by the way. And that discovery really set the stage for neutrino astronomy to start taking a real form. Neutrinos give us an entirely new way to look at the cosmos. They give us access to astronomical objects that light might not reach us from. And today's discovery is especially exciting because it teaches us more about our very own galaxy. We get to see the Milky Way in a way that we've never seen it before. So stick around. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. As you know, Shalma, I started a new job recently. I've been at Fermilab in the University of Chicago for almost 20 years. And I left those places a couple months ago and moved to the greener pastures of Madison, Wisconsin, where I'm a professor of physics up here, but also I direct this research center called WIPAC. WIPAC is involved in all sorts of things in high-energy astrophysics. We do a bunch of gamma-ray astronomy and cosmic ray physics, but at its heart is the world's biggest and most sensitive neutrino telescope, a telescope called IceCube. So I thought today we'd talk about the latest news from IceCube, which was announced last year. That announcement was that they had detected for the first time high-energy neutrinos, or neutrinos at all, that are coming from our own galaxy. Let's start by taking a step back and thinking for a couple of seconds about our place in the cosmos. You know, we live on this pretty typical rocky planet, more or less around a roughly average star. Sure, the sun's a little bit bigger and hotter than average, but, roughly in the middle range. And that star, the sun, is just one of, 100 billion or so stars that reside within the Milky Way galaxy. So the Milky Way is what we call a barred spiral galaxy, which means that its stars are distributed in kind of three different populations. There's, at the center is kind of a roughly spherical ball of stars, what we call it the galactic bulge. And then stretching out from the center throughout the galactic plane, the plane of the galaxy, are several spiral arms that give it the spiral pattern that you see. At least you would see that pattern if you could get out of the galaxy and kind of look down on it.
Yeah, I guess we haven't quite escaped the galaxy and taken a picture from up above like we have of the Earth.
Yeah, if we could travel at the speed of light for a few 10,000s of years, then we could get that nice picture. But no, it's not going to happen anytime soon.
But at the same time, we have images from Hubble and everything. We've taken pictures of other galaxies, so we've seen the spiral in action in other places. Like,
you can get a pretty good picture of, our nearest neighbor, M33, the Andromeda Galaxy. And this thing, that it's a lot like the Milky Way, it's in terms of size and structure and stuff. So that's a pretty good proxy for what the Milky Way is like. And then the third component of stars the Milky Way has is its bar. So the bar is kind of looks like a rectangular feature that stretches out from either side of the galactic center, in the same plane as the spiral arms. If you're having a hard time picturing this, I'd just Google images Milky Way, and you'll quickly find a picture of kind of what I'm talking about. The solar system, or our solar system, is located in one of the Milky Way spiral arms, and we're roughly 27,000 or so light years from the center of the galaxy. And from here, it's actually pretty hard to see the Milky Way spiral arms, bulge, or bar. We're kind of embedded in it. If you take a picture that we actually collect of the Milky Way, you don't get this kind of spiral arm, beautiful picture. Instead, you just kind of get this big, broad, diffuse band that spans across the sky. If you go out to the countryside on a moonless, clear night, you can see this. It's actually really gorgeous. So when we see that band of light across the sky that is the Milky Way, what that light is mostly coming from are a bunch of stars that are too faint for us to individually resolve with our human eye. But even if you took like a pretty simple telescope, you would start to notice that some of that faint diffuse emission is actually coming from individual stars. This is one of the first things Galileo learned, for example, when he started using his telescope to study the night sky. And if you use modern telescopes, you can resolve even much, much more of it. So in fact, this band isn't truly diffuse. It just is the illusion of being diffuse. It's actually coming from a huge number of distant faint stars. So I said before there are, in the ballpark of 100 billion stars or so in the Milky Way. But, that's not most of the total matter in our galaxy, or really most galaxies. About 90% of the total mass isn't stars, but is made of dark matter. And whereas the stars are kind of squeezed into this, galactic bulge bar and spiral arms, the dark matter doesn't follow that pattern. It occupies a much, much bigger volume of space, making up what we call the dark matter halo of the Milky Way. So whereas the extent of the spiral arms extends out to 50,000 light years or something like that, the extent of the Milky Way's halo goes to something like a million-ish light years.
I'm kind of curious about this. Is there an intuitive way to think about why, our spirals and the fact that the galaxy is basically flat, like all in one plane, it's because of the angular momentum, right?
Mm-hmm.
Of the galaxy, like in formation, gathering all of its stars and matter around the central black hole, and the spinning of all that stuff kind of flattens out. If dark matter, is subject to gravity just like everything else, why wouldn't the same thing happen to dark matter?
Well, if you took a individual particle, and by particle I could mean like a atom, but I could also mean a star or planet, those they're all functionally particles when you're talking about galactic dynamics. And you put it on some orbit around the Milky Way. Like maybe it's in the plane, but maybe it's not. It could be any kind of, orbit around that body. If it doesn't interact with anything, it will just stay on that orbit pretty much indefinitely. But if you start with like a spheroid or a spherical pattern of this stuff, it will stay spherical. The reason we have a galactic plane or disk and spiral arms and things is because those particles, quote unquote particles, can interact. So if you have some gas, those particles of gas can interact in ways that cause them to lose energy. And when they lose energy, their angular momentum flattens them into this plane.
Does this suggest then that dark matter, wouldn't analogously clump up like normal matter does?
Exactly, yeah. I mean, dark matter, it forms clumps, but not in the same way that stars and planets do. At least if dark matter really is feebly interacting and all that like we usually take it to be, then we shouldn't expect there to be like big, dense collections of dark matter anywhere. To the extent that there are clumps of dark matter, those clumps are big and relatively diffuse clumps.
So let's get back to the Milky Way, the galaxy we call home. But let's keep zooming out and put us into even more context.
The Milky Way is only one of roughly 1 trillion or so galaxies that are contained within the observable universe. Our closest neighbor galaxy is Andromeda, which is 2.5 million light years away. In most respects, Andromeda is a lot like the Milky Way. And the Milky Way and Andromeda are the two biggest members of what we call the local group, which is kind of like a small cluster of galaxies. There are roughly 80 or so, galaxies in a local group, but most of them are really small, kind of miniature galaxies. The local group, in turn, is part of an even bigger thing called the Virgo supercluster, which is a group of different galaxy clusters all bound together. So it's like a cluster of clusters. It includes the local group and the Virgo cluster of galaxies and another 100 or so other galaxy groups and clusters. So this is like one of the biggest structures you will find in the whole observable universe. So if you go out to the countryside on a moonless, clear night and look at the night sky, you're going to see that the Milky Way is a fairly prominent feature. It might not even look like you're seeing an arm of a spiral, but what you're seeing is that band of unresolved stars, most of which are like pointed in the general direction of the galactic center, roughly in the galactic plane. And this is kind of exceptional because if you think about it, almost everything you can see with the naked eye is a pretty nearby object, astronomically speaking. You can see the moon, you can see 5 of the planets. A lot of the planets you can't see, but you can see 5 of them. obviously the sun. And then you see the stars that you see in the sky, but these are all pretty local stars. These aren't, astronomically speaking, very far out of our backyard. The, Milky Way is really the thing you can see that's the farthest away easily. I guess there's one exception. You can see the Andromeda Galaxy with your naked eye, and that's a little farther away. But basically, those are the two really distant things you can see without using a telescope.
With telescopes, we can see a lot more. Like we mentioned before, you can resolve the milky-looking arm into all those individual stars. But even more interesting than that, you can collect light from frequencies outside of the visible range. Light you wouldn't be able to see with your eyes anyway.
You can Google multi-wavelength sky and you will see pictures of the Milky Way in visible light, in infrared light, in ultraviolet light, as well as X-rays, microwaves, radio waves, gamma rays, all these things. And astronomers use all these different kinds of light because they all kind of teach us slightly different things, or sometimes dramatically different things about what we're making images of. For example, infrared light is really useful because it's not easily absorbed by dust. So you can look into big dusty areas, like you can look through those dust clouds with infrared light in a way that you can't with visible light. Gamma rays are really important because they're only produced in really high energy environments. So you kind of get deep into the heart of the most volatile areas looking in the gamma ray band and so on and so forth. But if you look at all these different images, the visible, infrared, gamma ray, microwave, radio, whatever, you kind of see the same thing, a big band of light stretching across the inner part of the Milky Way in this kind of big, broad, diffuse pattern. But last year, astronomers detected the Milky Way in an entirely new way. We've been doing this with light for a long time, but now, for the first time, we've detected it not using light, but using these particles called neutrinos. Unlike other known forms of matter or energy, neutrinos don't really interact with anything much at all. And this is important because it allows them to travel through really dense regions of matter, usually without interacting. So neutrinos can easily pass all the way through the Earth without doing anything, basically. At relatively low energies, they can even pass through the sun. I think last year we talked about an observation by the IceCube telescope where they saw neutrinos from close to a supermassive black hole around a nearby galaxy. And, those neutrinos made it through some really dense, highly energetic material to escape. And that's just not something that any other form of matter can do. So neutrinos are kind of uniquely well suited for probing dense environments to astronomers.
This is really the power of neutrino astronomy. For example, imagine we wanted to probe into the core of the sun. If you point any normal telescope at the sun, no matter what frequency you're using, you're really only going to see the light from the bright surface. You're not really going to see past the surface into the core of the sun.
But if I point a neutrino telescope at the sun, especially one designed to detect relatively low energy neutrinos, I get a picture, I get an image of the neutrinos coming from the core of the sun through nuclear fusion. Only neutrinos can do that. Nothing else gives us a picture of the inside of the sun or other sorts of concealed, regions behind thick layers of energy and matter.
Light at the end of the day is also a particle, right? The photon, and it's characteristically the same as taking a normal image where you're actually just collecting a bunch of particles, which are photons, and drawing a picture with that. It's the same, but you're switching out what the particle is.
Exactly. A modern astronomer always thinks of light as a kind of particle. And sometimes we really detect the photons one at a time. And that's true, for example, when you're using something like a CCD camera, a charge coupled device or something, where that photon hits your electronics and lights it up, And then other times, like, you might be using some sort of radio antenna or something, and you don't think of it as individual photons then, but deep down, it's still individual photons. All right, so let's talk a little bit about how we detect neutrinos. So if you're picturing the IceCube neutrino telescope, and you're thinking in terms of telescopes like everyday, conventional telescopes, you're definitely picturing the wrong thing. IceCube is nothing like a normal telescope. It doesn't have any lenses or mirrors, and it doesn't focus anything. Like, that's not what it does. The detector medium, the thing that IceCube is built around, is a big piece of Antarctic ice located just below the South Pole. So to build IceCube, teams of scientists went to the South Pole, and they used a hot water drill to dig holes by melting ice deep into the below the ice surface. These holes extend about 2.5 kilometers deep. And then into those holes, they lower strings of detectors. So the detectors, think of them as kind of like round or oval pieces of electronics, roughly a foot or 2 feet in diameter, something like that. And then the cable is a electrical cable, but it also supports the string of detectors. And you lower the detector string in there, and then the ice freezes, or the water freezes again, holding those detectors in place. And voila, you've got yourself part of a neutrino detector.
It's really ingenious.
I think so. I recently learned a ton about the details of how like the cables and the optical modules and the ice drill work. And it is so sophisticated. They really thought about everything. And as a theorist, I rarely, concern myself with such things. But the more I learn about it, the more I am impressed by my experimentalist colleagues. So IceCube consists of about 80 of these holes filled with strings. Okay, so 80 different strings of these detectors forming this giant array that span about a full cubic kilometer of ice. So it's an enormous neutrino detector consisting of all these detectors spanning across this cubic kilometer of Antarctic ice. So how does this actually work? How does this tell us something about neutrinos? Well, most of the time when a neutrino reaches the IceCube telescope, nothing happens. The neutrino passes through and there's nothing to see, no interactions take place, and we don't see those neutrinos. But a small fraction of the time, a neutrino will travel in or near the IceCube's volume, and it will interact with one of the atoms in that ice. And when it does, it can produce high energy particles like, muons is one example, or even just showers of particles. And IceCube's array of detectors can detect that. So when that neutrino comes in and hits that atom and gets transformed into a muon, that muon then travels in an approximately straight line through the detector, depositing energy that whole time and leaving what looks like a track through the detector. So we can reconstruct the energy of that track and the direction it came from and infer from that the direction and energy of the responsible neutrino. Other kinds of neutrino interactions hit that piece of ice and just deposit energy in the kind of a roughly spherical pattern in all directions. We call that a shower. And to some extent, we can reconstruct the direction that those neutrinos came from too, not quite as precisely as with muons, but we can still figure out, we think that one's from a neutrino, and we think it came from that direction. So IceCube has been detecting neutrinos from space, very high energy neutrinos, for more than a decade now. But we still don't really know where most of these neutrinos come from. We do know that most of them don't come from the Milky Way, okay? So like I said, if you look at the night sky in visible light or any other kind of light, the Milky Way is really prominent. That's where most of the light seems to be coming from. This is not true in neutrino astronomy. Most of the neutrinos that IceCubes see look like they're pretty isotropic on the sky, so they're coming from kind of all directions roughly equally. And this, is indicative of the fact that they're not coming from our galaxy, but from throughout the cosmos. This is a extragalactic, background of neutrinos, and they're probably coming from all sorts of different objects scattered throughout the cosmos. We know at least some of the neutrinos are coming from supermassive black holes in other galaxies. So far, there have been 2 of these sources we've detected. Well, 2 or almost a third one. There's a third one that looks like we're maybe starting to detect it. One of them is called NGC 1068. We did a whole episode on that. There's another supermassive black hole called TXS 0506 plus 056. I know we're great at naming these things in astronomy. But that one probably is also producing very high energy neutrinos. But that's only a tip of the iceberg. We don't really know where most of these neutrinos come from. When it comes to the Milky Way, until recently we hadn't detected those neutrinos. But we knew that it had to make some neutrinos. After all, cosmic rays exist. These are charged particles like protons and nuclei reaching Earth all the time. And we detect these things across all ranges of energy, down from, relatively slow-moving particles all the way up to the highest energy particles we've ever observed in the universe. It's about 10 to the 11 GeV, or gigaelectron volts, is the highest energy cosmic rays. For context, at the Large Hadron Collider, the most energetic particle accelerator human beings have ever made, they're making things that are, 14,000 gigaelectron volts. Or actually, that's when two collide. So really 7,000 gigaelectron volts. And that's tiny compared to what nature makes for us in the form of the highest energy cosmic rays. So we know these cosmic rays are out there. And it's completely clear that whatever makes those cosmic rays has to make neutrinos too. Those cosmic rays are going to hit stuff. By stuff, I mean gas or maybe background light. And they're inevitably going to, in those interactions, produce things we call pions. And then those pions decay to make neutrinos. There's just no way around that conclusion. And in addition to the sources themselves of the cosmic rays making neutrinos, all those cosmic rays just traveling around through the Milky Way in any given day, those could also interact with things like gas to make neutrinos. So there should be two kind of components. There should be neutrinos that come from the individual sources of the cosmic rays in the Milky Way. And then there should also be a fuzzy, diffuse pattern of neutrinos coming from the cosmic rays interacting as they kind of dance around throughout the interstellar medium of the Milky Way.
Last year's discovery is more than just a chance to take a cool picture of the Milky Way. It's also a chance to learn more about where the cosmic rays raining down on us come from.
Despite the fact that we know cosmic rays exist, we've known that for more than 100 years. And despite the fact that we have some notion of what kind of things might make cosmic rays, we really don't know where they come from. A lot of astronomers and astrophysicists, and I'd include myself in this category, think that probably supernova remnants are part of the story. These are the kind of things that are left behind after a supernova. And for some tens or maybe hundreds of thousands of years, these things could maybe accelerate particles to pretty high energies and make cosmic rays that way. And there's some indirect evidence from gamma ray telescopes saying that that's probably going on. But we really don't know if that's the whole story or part of the story, or, it's still a huge open question exactly where the cosmic rays come from. And you might think this would be an easy question. After all, like I said, we've been detecting cosmic rays for more than 100 years. But cosmic rays don't move in straight lines. So when you see a cosmic ray, you don't know where it came from. It's kind of like standing blindfolded in a room and you smell something and trying to guess what direction the thing comes from. So, where is that delicious food that I'm smelling? Those odor molecules diffuse around through the air. And by the time they reach you, they're not coming mostly from the direction of the food. They're coming from all directions. So you lose directional information when you use the sense of smell. And the same is true with cosmic rays. These charged particles kind of random walk and diffuse through the galaxy. And when they reach us, the direction they come from doesn't tell us much about the direction of their origin.
What's deflecting them in this case?
Yeah, magnetic fields. So the interstellar medium is full of a complicated, tangled series of magnetic fields. They're about a microgauss in strength, if that means anything to anyone. But that's strong enough to deflect particles on the kind of scales we're talking about. And it is like a true random walk how these particles make their way through that tangled magnetic field. The metaphor of, odor molecules moving around through a room is actually pretty spot on when you're considering the propagation of cosmic rays. So you can't learn where the sources of cosmic rays are from the cosmic rays themselves. So you might think you'd want to use a gamma ray telescope, because gamma rays, of course, travel in straight lines. So you could maybe point the gamma rays at the sources of the cosmic rays. But the problem is that gamma rays are not only made by protons and nuclei, but they can be made by electrons too. So just because you see a high energy gamma ray doesn't tell you that you're looking at a source of cosmic rays. You could just be looking at an ordinary source of high energy electrons. So you can learn something from gamma ray telescopes in this respect, but you can't really be sure that you're looking at cosmic ray sources from gamma rays alone. So if cosmic rays themselves won't tell us where these particles come from, and gamma rays are at least not going to do it unambiguously, we need some other way to do it. And the solution to this conundrum is neutrinos. Unlike cosmic rays, neutrinos are not deflected by magnetic fields. They just move in straight lines.
Because they're neutral.
Yeah, they're electrically neutral. And then, unlike gamma rays, neutrinos, at least at high energies, are only made by protons and nuclei. So if you see a high energy neutrino coming from some direction of space, you can be sure that a cosmic ray made that neutrino. There's just nothing else that could do it. And if you were to see a point source of neutrinos from somewhere in the Milky Way, you could be really sure that that is a source making cosmic rays that are at least part of the cosmic ray spectrum we see here on Earth.
Okay, so this discovery of galactic neutrinos was poised to help us answer the question about where all the cosmic rays really come from, because neutrinos are probably coming from the same places. So what did we find? Where are these neutrinos coming from, and how did this discovery change things?
What did we expect before IceCube saw these neutrinos from the galactic plane? Well, we thought that, there could be neutrinos from individual sources. I mentioned supernova remnants before. That's probably our leading candidate for what might make neutrinos in the Milky Way. But there are also things called microquasars, which are relatively small black holes, maybe 10 times the mass of a normal star or something. And they'd be accreting matter onto them, making energetic beams of particles, and these might be able to make neutrinos. Relatively young pulsars could maybe also make neutrinos. And, a hot topic has been maybe the supermassive black hole at the center of the Milky Way. Could it maybe make neutrinos? Any number of these things were going to be high profile, things to look at once you had a sufficiently big and sensitive neutrino telescope. But then in addition to all these point sources, there's just going to be the diffuse emission that's produced as the cosmic rays travel through the interstellar medium of the Milky Way, and those cosmic rays interact with gas. So you should expect a big fuzzy band of neutrino emission from the galactic plane from that sort of process as well. The problem is that although we were pretty sure all these neutrinos should exist, we also had not really expected the signal to be very bright. And because you can't use muon tracks very easily in the southern sky, and the showers don't point in very accurately at the directions of the neutrinos, it just looked like this was going to be really hard. If you asked me a couple of years ago what kind of neutrino telescope it would take to see the galactic plane, I'd probably tell you you'd need something quite a bit bigger than IceCube, or maybe something in the northern hemisphere where you don't have the same problems. I didn't really expect this to happen anytime particularly soon, but I was wrong. Despite all these very real challenges, the IceCube collaboration published last year in 2023 their first detection of neutrinos from the plane in the Milky Way. The statistical significance of this detection is about 4.5 sigma, or standard deviations, which is just slightly below the gold standard of discovery at 5 sigma. But I'm perfectly happy to call this a discovery. For all intents and purposes, we're sure this is real. This is not going to be some sort of statistical fluke. But I would say that despite this huge discovery, there's still way more questions left unanswered than answered by it. We still can't tell whether we're looking mostly at diffuse emission from cosmic rays interacting in the interstellar medium, or maybe there's a bunch of point sources. We can tell from the data that it's not just coming from one source or 2 or 3 sources, but could it be coming from 20? Sure. Yeah, we can't tell that apart yet. With more data, we should be able to do this a little bit better. I look forward to learning what a northern hemisphere telescope might be able to tell us about the galactic plane. I look forward to what the IceCube upgrade, which is the planned improvement to IceCube, might be able to have to say about this once it gets installed next year. This is going to be a topic that keeps coming up in high-energy astrophysics and multi-messenger astrophysics. This is just the beginning. It is definitely not the end.
Why This Universe is produced and edited by me, Shalma Wegsman, and our co-host is Dan Hooper. Dan is a professor of physics at the University of Wisconsin-Madison and the director of the Wisconsin IceCube Particle Astrophysics Center. If you like our show and you want to support us, you can join us for as little as $3 a month on Patreon. There you can also get access to exclusive Ask Us Anything segments where you can directly ask Dan and I any of your questions on physics or whatever else. And to find that, just go to patreon.com/whythisuniverse. As always, thanks for listening.